Uh, my name is Sai. I'm a postdoctoral fellow with Dr. Adbags at National Institutes of Health. So I'm working on pressure jump NMR spectroscopy of a protein that undergoes oligomerization. As Ruth rightly mentioned, and it is recently tweeted in the Twitter handle of ICMRBS, where it states that the pressure jump NMR with a protein that I have never heard of. Honestly, I should agree on that. And till last year, I have never heard about this protein, and we got introduced to this protein by an X-ray crystallography group at the National Institutes of Health, as they could not obtain structural information on this protein using both X-ray or cryo-EM. They approached us to obtain some structural features of this protein. So what is this protein? What is the role of this protein? This protein is involved in the formation or the maturation of the enamel, of the dental enamel. So here is the vertical cross-section of the tooth, highlighting the enamel, which is the outermost white layer of the teeth. And this dental enamel is the hardest tissue in the mammals. This is comprised predominantly of the hydroxyapatite mineral, which is composed of calcium and phosphate ions. So in addition to this amelotin, there are other three proteins that are involved in the formation of enamel, whereas amelotin is recently discovered in the year 2005. And as there is very limited structural information on all these proteins that are involved in the enamel formation, so far we could not understand how the dental enamel is formed. So before getting into the structural information, we went ahead and looked at the AlphaFold database for the amelotin structure, which is available in the DeepMind database. I think many of you must have come across this AlphaFold. This has recently revolutionized the structure prediction algorithm. And in this database, there is almost all the structures available for all the proteins. Nevertheless, this is the structure of the amelotin that is deposited in the DeepMind database, where it is predominantly a random coil structure, and there's a small helical segment of about 15 amino acids. And the bottom panel shows the PLDDT score for this protein, which has a scale of 0 to 100, where 100 being the more confidence in the structure prediction. And according to this AlphaFold program, the score of about 70% suggests that this is the high confidence structure. However, as you can see, all the residues have a PLDT score below 50, suggesting that this is a very low confidence structure generated by the AlphaFold model. So moving into the experiments, this amelotin protein is about 200 amino acids in length, and it consists of about 24 proline residues. In solution, amelotin spontaneously adopts into oligomers, and this is the dynamic light scattering profile of the amelotin, showing its polydispersive nature with an average diameter of about 13 nanometers. The figure on the right shows the NMR spectrum of the amelotin at the atmospheric pressure of 1 bar under physiological conditions of pH 7. Of the expected 200 amino acids, we observe only few resonances. Now that we know that it forms oligomers, the resonances that we observe in the spectrum belong to the flexible residues of these oligomers. And it is very well known that these oligomeric proteins, due to their thermodynamically low stable, they undergo dissociation in the presence of the hydrodynamic pressure. Indeed, with the application of 2 kilobar pressure, we could see the dissociation of the oligomers into monomers of the amelotin, and we can observe almost all the 200 amino acids at high pressure. So based on the pressure titration from 2000 bar to 1 bar, we could find out that these visible resonances in the NMR spectrum at 1 bar belongs to the residues of 1 to 25 and the C-terminal 60 residues, suggesting that these are the flexible residues of the amelotin, whereas the central region of about 25 to 130 amino acids form the core of the oligomers. Now, to reduce the spectral overlap and also to simplify the NMR analysis, we have truncated this amelotin by removing the flexible tails at both the N and the C terminus. That resulted in a truncated construct, which comprises of 25 to 130 amino acids. Unfortunately, this truncated construct heavily precipitates in the under physiological conditions of pH 7. So we had to perform our NMR experiments and other experiments at slightly acidic conditions of about pH 4.6. Interestingly, even under these acidic conditions, this truncated construct forms oligomers similar to that of the wild type under physiological at pH 7. So similar to the full length at 1 bar, this protein, the truncated construct in the HSQC reveals only very few resonances of the expected 120 amino acids. And again, similar to the full length protein, at high pressure, we observe dissociation of the oligomers into monomers, and we can observe almost all the resonances at high pressure. More importantly, this pressure denaturation is a reversible process, and we can switch multiple times from high pressure to low pressure, and we can obtain the oligomers. We can obtain reversible oligomerization by going to low pressure, and again, dissociation of the oligomers by going to high pressure. This allowed us to perform NMR experiments using the high pressure NMR experiments by rapidly switching to high pressure and low pressure. And this is apparatus that is recently developed in our, that was developed few years ago in our lab in collaboration with Dr. Philip and Finruth at the NIH. The high pressure NMR experiments are conducted in a zirconium NMR tube, as this high pressure NMR tube can withhold the pressures of up to 3 kilobars. So this high pressure NMR tube is mounted onto in the NMR probe, and it is connected to by a stainless tubing to a valve at high pressure that operates at high pressure, and also the valve that operates at low pressure. By turning or switching the low pressure or high pressure valves, we could switch between 1 bar to 2.5 kilobar in a span of about a couple of milliseconds. So to obtain this secondary structural information of the oligomers that are otherwise invisible at 1 bar for, at ambient pressure of 1 bar, we performed pressure jump NMR experiments where we measured the 15N chemical shifts of the oligomers using this stroboscopic experiments, and the pulse sequence is shown here. This pulse sequence is originally published in the JACS paper in the 2018 previously by our group, and this is a small modification to the earlier publication, where at a high pressure, the protein, and the majority of the experiment is conducted at high pressure, and the protein is allowed to fold or oligomerize by in a few milliseconds of 300 milliseconds, where it is rapidly switched to the 1 bar. And this is the stroboscopic element that we incorporate in the regular HSQC experiment, which consists of 290 pulses that are separated by a delay of about few milliseconds, of about 1 millisecond. So this experiment, this two-dimensional experiment is conducted in a pseudo 3D fashion, where in one half of the FIDs are collected with a 90 minus X phase, and the other half of the FIDs are collected with a 90 Y phase. So due to which we can obtain the intensities in the two spectrum that are modulated either by the cosine omega n or the sine omega n modulation, where the omega n is the chemical shift of the nitrogen chemical shifts at 1 bar that are sampled here. And the average weighted nitrogen chemical shifts are obtained as an intensity of both the spectrum by the ratio of the intensity between the two spectrum. And these nitrogen chemical shifts were plotted along the residue number. And here is the y-axis is the delta 15N, which is the 15N chemical shifts measured from this formula that is under experimental condition. And this is subtracted from the 15N chemical shifts under high pressure. As we can see, majority of the residues around the region 100 to 120 experience large chemical shift changes, suggesting that the chemical shifts at 1 bar are for this region are predominantly different when compared to the chemical shifts at high pressure. And also we see small chemical shift changes for the region 80 to 100 amino acids, and also for 35 to 55 amino acids. So to obtain more specific secondary structural features, we extended the experiment by collecting the carbonyl and C-alpha chemical shifts, which is shown in panels C and D. So the deviation of the chemical shifts that are positive indicate that the protein can adopt the alpha helical structure, whereas the negative chemical shifts suggest the propensity of the formation of the beta strands. As you can see here from the carbonyl chemical shifts, and both the carbonyl and C-alpha chemical shifts are positive for the amino acid stretch of 106 to 117 amino acids, suggesting that this region adopts alpha helical structure in the oligomeric state. And negative values are observed for the region 88 to 100 amino acids, suggesting that this region can adopt into 2 beta strands. And also, small negative values are observed at the N-terminal region, suggesting that these 2 regions can also adopt 2 beta strands. Overall, under oligomeric conditions, the amelotin protein adopts into, has secondary structures of 4 beta strands and an alpha helical structure. So in order to obtain how rigid these oligomers in this short span of oligomerization state, so we obtained 59 T1 and T2 times of this relaxation times of the oligomeric state at 900 megahertz spectrometer. So here is the pressure jump pulse sequence scheme for the T1 experiment, where it is briefly allowed to fold at 1 bar for a span of 1.4 to 2.8 seconds. And the pressure jump T1 times are plotted for, are shown in the blue color. And these are significantly higher when compared to the T1 relaxation times of the protein that are collected under static pressure, complete static pressure, where it undergoes complete monomerization. And these T1 times are inconsistent with the secondary structural information, where this region has higher T1 relaxation times when compared to the monomeric protein. And also we can observe the similar trend of higher relaxation times for the oligomeric species when compared to the random coil structure. Similarly, we also obtained the R2 relaxation rates recorded as the R1 row relaxation times with the 2 kilohertz spin lock field. And similarly, we observe higher R1 rate, higher R2 rates for the secondary structural regions that are of secondary structural elements at the C-terminal and the N-terminal region, whereas the central part of the protein and also the extreme, the C-terminal tail, has low R1 row rates, suggesting that these 2 regions are extremely flexible. However, the R1 row values at the 900 megahertz of about 120 second inverse corresponds to a tau C of about 70 to 80 seconds for a and the T1 times for this oligomeric state, however, corresponds to fairly smaller oligomeric species of about 50 nanoseconds. This is quite contradictory. However, these T1 rates are rather nullified due to, as the oligomers that formed in the span of 1.4 to 2.8 seconds are indeed not very rigid, and they are quite flexible oligomers. So that's why we would see a decrease in the T1 values for this oligomeric state. Now that we have obtained secondary structural information and the relaxation times, we went ahead to obtain the distance restraints using the nosy-based experiments. So this is measured as NNH nosy. The figure on the left shows the nosy strip of the segment containing 106 to 117 amino acids that is collected at a static pressure of 2 kilobar, where the protein is substantially a monomer or adopts a random coil structure. The diagonal peaks are shown in black color, whereas the NOE cross peaks are shown in the cyan color. As expected, for a random coil structure, we do not observe long-range NOEs, and we observe only weak NOEs for I+1 or I-1 residues. So in a similar experiment that is performed using a pressure jump approach, where the protein is rapidly allowed to fold at 1 bar during the NOE mixing time of about 100 milliseconds. And the similar strips are shown on the right for the pressure jump experiment, where we can see now the NOE cross peaks that are shown in the blue color. And here we can see the NOE cross peaks for up to I+1, I+3 to or I-3 residues, suggesting that this peptide stretch of 106 to 117 amino acid adopt alpha helical structure, which is consistent with the previous slides where we have shown that it adopts alpha helical structures. So the comparison of the NOESY spectrum between the static pressure and the pressure jump clearly demonstrates that these NOEs that we observe in the pressure jump are for the oligomeric species. And to the best of our knowledge, this is the first time we are demonstrating NOEs in an aggregated state in solution state. In addition to the medium range NOEs that we observe in this polypeptide stretch, we also observe long range NOEs, particularly in this beta strand stretch of about 80 to 88 to 100 amino acids. And here we can see the cross peaks for the 88th amino acid to 100th amino acid, where here we see the NOESY cross peaks for this 2 amino acids, and 90 to 98, and also 92 to 96. And these 3 NOEs define the beta tone for this polypeptide stretch. Although using this NOE experiments, we could demonstrate the long range NOEs, it is very difficult or challenging to obtain a high resolution structure from this purely from the NOE experiments, as we don't have any homology model. So we took advantage of the AlphaFold recent developments in AlphaFold, that is the AlphaFold multimer module. And we generated the AlphaFold hexameric structures, which resulted in several models from of about 25 structures, and all the structures are quite different from each other. So we asked if we can pick the right structure that is consistent with our NOESY experiments, so that we can select a few structures and exclude the structures that are inconsistent with the NOESY experiments. So here the figure here shows a monomeric structure which is taken from the hexameric structure, and we can see the amide NOEs that are less than 5 angstroms for this beta strands, and we can observe these 3 NOEs. And these 3 NOEs are consistent with these 3 distance restraints are consistent with our NOESY spectrum, suggesting that this model is consistent with our NMR experimental data. Whereas on the other extreme, model 19, the distance restraints or the amide distances are inconsistent with our NMR structure, suggesting that this model is inconsistent with our experimental data. So we are in the process of, and another point to mention here is this multimer model is generated for a small fragment of about 83 to 122 amino acids, whereas by extending the multimer model by incorporating all the amino acid, we could not obtain the right model structures. So we are in the process of validating this structure and also extending these multimer structures to the entire full-length protein. So in summary, I would like to summary of our experiments is that amelotin forms oligomers in solutions with the residues 25 to 130 forming the core of the oligomer. Using stroboscopic experiments, we demonstrated that this amelotin protein adopts 4 beta strands and 1 alpha helical structure, and long-range distance restraints were obtained using pressure jump NOESY experiments. The pressure jump NOESY experiments in combination with AlphaFold multimers will be now utilized to derive the structural model of the amelotin. And more importantly, these methods that we demonstrated here could be applied to other large oligomeric aggregated systems such as A-beta or other amyloidogenic proteins. So at the end, I would like to thank Adbax for his continuous support and mentoring throughout the project and all my postdoctoral stay. Yang for helping me with the AlphaFold multimer model generation. Phil, James, and Jinfa for assisting me with the pressure jump apparatus and other NMR experiments, and Dr. Gremi Visto and Dr. Sagar Vatsala for from the National Eye Institute for introducing us to this amelotin protein system.